NanoHub U, online instruction.
Welcome back to Unit 4 of our course on quantum transport, and this is the 5th lecture. Now, in this lecture, we want to talk about some of the spin-dependent properties of the channel that come in through this H. Like in the previous lectures, in like 2 and 3, we talked about magnetic contacts and how the spin-dependent properties enter through the self-energies. Now we are talking about the channel. Now, in this context, first want to remind you, like this is something we talked about in part A and also in part B, that usually when you're talking of electrons in vacuum or in atoms, you have a Hamiltonian where this mass is the free electron mass. Now, electrons in solids, of course, in general, its description is much more complicated, but the simple description that we have largely been using for our examples involves this effective mass model, where they are described by a band whose band edge is at EC and whose mass is not the free electron mass m0, but rather the effective mass m. And of course, there is no simple way to derive this from this. And this is not general either. You may have many bands, you might need a more complicated description. But what we have been using for our examples is the effective mass model. Now, in this lecture, what I'll try to show is that when you consider electrons in vacuum, I'll try to explain how the spin orbit correction comes about. And this requires you to take the original Hamiltonian multiplied by I being this identity matrix, 2 by 2 identity matrix. Just as earlier, I took a simple one-level model, said if the level is epsilon, then when you include spin, it becomes epsilon I. Similarly, this part kind of becomes what we had before times I. And then there is this additional relativistic correction, which is what I'll try to explain. That's called the spin-orbit coupling. And this involves these Pauli spin matrices that we have introduced, the sigma, and this F is the electric field. So what I'll try to explain is this relativistic correction and where it comes from. Now, in solids, this though is in vacuum or in atoms. Now, in solids, there's a similar term. But of course, again, in solids, the general description could be much more complicated. But within this one-band model, if you consider a conductor in the xy plane so that this z direction is normal to it, then you would have a term looking like this, which is often called this Rashba spin orbit term. And that's what we'll consider, remembering again that in general electrons in solids may require or you may want to use more sophisticated models. Okay. So what we'll be talking about then is largely about this term, and electrons in vacuum and what this correction is about. So as I mentioned, this is what you call a relativistic correction, which means originates from this relativistic effect. Now, the non-relativistic energy momentum relation is E equals P square over 2m. That's the semi-classical equation, and the Hamiltonian you use in a quantum description is obtained from this by replacing the P with the P operator or the momentum operator. And as you know, this leads to this dispersion relation, the EK relation, where instead of P, if you put H bar K, you'll get the EK relations. So this is what we have generally been doing. Now, the relativistic energy momentum relation looks like this. So if you put momentum equals 0, you get E equals mc square, the most famous equation in the world, I guess. And then when the momentum is non-zero, that's when there's this additional term. Now the question is, how do we write down the corresponding Hamiltonian, the H matrix? Because if I turn the P into an operator, I have a problem because you see, I need the operator corresponding to the square root of this. And having an operator under a square root is not very convenient, right? Now, this is where what Dirac showed was that you could write a matrix like this, which this is actually a 4 by 4 matrix in the sense, although it looks 2 by 2, but if you look up here, it's mc square times I, and I is the 2 by 2 identity matrix. Minus mc square I, that's again a 2 by 2 matrix. And this is the sigma dot p, sigmas being the Pauli spin matrices, and those are again 2 by 2 matrices. So each one of these is a 2 by 2 matrix. So overall it's a 4 by 4 matrix. And what Dirac showed was that this matrix, if you multiply it by itself, you will indeed get that number times a 4 by 4 identity matrix. So in some sense, it's like the matrix square root of that. So just to see that, what you have to do is multiply it out. So multiply this with this. So then what you get is, if you look at, say, the 1, 1 term, m0 c square I, m0 c square I, that's like m0 square c to the power 4 I. Then you have c sigma dot p and again c sigma dot p, and that's where you have to make use of this identity that I believe I've stated earlier, that for any vector v like this, sigma dot v1 times sigma dot v2 can be written as the sum of these two terms. And in this case, if v1 and v2 are both this operator p, then you see sigma dot p times sigma dot p becomes this p dot p, which is p square I, and p cross p, which is 0. So this times this becomes like c square p square times I, and so it adds up and gives you that quantity times I. Same with the 2, 2 element, whereas if you look at the off diagonal, this one, you get something like this times this plus this times this, which is exactly the negative, and so it cancels out. So here you get this, what I've written as Z, which is like a 2 by 2 zero matrix. So this, of course, is identity zeros here. That's basically the 4 by 4 identity matrix. So bottom line is, this H is kind of like the square root of that in a matrix sense, right? Now, so this is the Dirac Hamiltonian, this that we just wrote down, and it corresponds to an energy dispersion relation that corresponds to this relativistic one. And if you plotted it, it would look something like, when k is 0, the energy would be mc square, and then as k increases, the energy would increase like so. Now, if you want to use this, like the Dirac equation, if you want to use this to describe systems, then you see you have a 4 by 4 matrix and you need a wave function with 4 components, which I've written as psi and phi. The psi itself is a 2 component quantity, phi itself is another 2 component quantity. Now, what we commonly use though is not a 4 component wave function, but a 2 component wave function. And that is this non-relativistic approximation that one makes. Let me explain the idea a little bit. So actually, if you looked at the energy here, you'll notice there's a plus minus, because when you take the square root, it's a 4 by 4 matrix. So when you look at the eigenvalues, you'll find 2 of them are up here and another 2 down here. And initially, of course, this caused a lot of debate because, how do you interpret all these negative energy levels? And the accepted picture that people have these days is that in vacuum, where there is nothing, that corresponds to all these energy levels being completely filled up. So even when there is nothing, these are all filled up. And then if you have a few extra electrons, those are the ones that we normally see out here. And an important experimental consequence of this picture is that if you hit this with light whose energy corresponds to bigger than 2 mc square, then it can knock these electrons out from here over here, leaving a hole behind. And that's what's called a positron. That's this anti-electron. And these have been experimentally observed, very real things. But usually, of course, you're not hitting it with light with such huge energies, because mc square, if you work out, then if you put in the numbers, the free electron mass, the velocity of light, then in units of electron volts, it would come out to be about a million electron volts or 500,000 electron volts. So this is a very huge energy. And so normally you're not hitting it with light with that kind of energy. And so most of the time, all the physics we see is electrons out here. And this is largely sort of filled up. Now, if you look at the wave functions of electrons out here, the thing is, it is largely psi with a little bit of phi in it. Whereas the wave functions here is largely phi with a little bit of psi. And the reason you can see, if you put p equals 0, then you see the mc square, that's the top band, that corresponds to the first two components. So psi, E psi equals mc square times psi if the momentum is 0. And E phi is minus mc square times phi. So this is largely phi. So as long as we are talking of relatively low energy electrons out here, you can use this simplified description where you keep only the one component. Of course, you cannot just drop it because that wouldn't be right. What you could do is this idea that we had used in Unit 3 for calculating self-energies. You see, there the argument we had is, supposing we had a device described by H and a contact described by HR, and they are connected by this matrix element tau, then you could replace this, you could get rid of the contact and write E psi equals H plus sigma psi, where the sigma is given by this tau G tau dagger. Right? This is the general method for calculating sigmas. Here, of course, we are not talking of contacts or anything, but you could use the same idea. You could evaluate a sigma. You see, what you want to do is keep this and get rid of this part. So what you could do is calculate a sigma, which is tau, that's sigma dot p, G, which is this E minus mc square plus u, so that's E plus mc square minus u, inverse, and then tau dagger, which again is sigma dot p. So that would be the sigma, and this we could add to whatever we had here, and that would be our effective Hamiltonian. But now it would be 2 by 2 instead of 4 by 4. So instead of the actual Dirac Hamiltonian, which is 4 by 4, you could use something like this. This is the reduced Hamiltonian, which is 2 by 2. And there we have added in this tau G tau dagger type of term. Now, this requires some discussion then in terms of how to handle it when you have a potential that is varying with energy, varying with spatially and so on, because you see, this itself is a matrix. But what you could do is, one approximation we could make is, we could say that, well, in this quantity here, we'll replace E equal with just mc square, with the idea that, you see, we are interested in energy levels up here, energies up here, and that's almost mc square, and a little bit, but nearly mc square. So if you do that, this becomes 2mc square. And so it goes to there's an inverse, so that's 2mc square, and the c square cancels out the one we had before, and so you get this. You see? And this, using this identity I had mentioned before, sigma dot v1 times sigma dot v2, and in this case, the v1 and v2 are the same vector, that just gives you p square over 2m times I. And that's our usual non-relativistic answer. So this is what you get if you do the crude approximation of putting E equals mc square. But if you try to evaluate this a little more carefully, I mean still approximately, but a little better approximation, then you get this spin orbit term. This is this relativistic correction, that the first order correction to this non-relativistic result. And I'm not going into the details of how you'd get from here to here, but the point to note is this involves the electric field F. And the electric field is related to the gradient of U, because U is the potential, field is the gradient of that. Now, one way to I guess, understand this, or I guess one related result that might give you a little more insight into this term is something like this, that if you wanted to include magnetic fields, then as we discussed in Unit 3, magnetic fields require a vector potential A. The B is this curl of A. And in the Schrodinger equation, P gets replaced by P plus QA. And so, if you include magnetic fields, then in the Dirac equation, P would get replaced by P plus QA. And so when you calculate the reduced H, you'd get something like this. And this with a little algebra, I mean, it's not obvious, takes a little algebra to get there, you can show is actually P plus QA dot P plus QA over 2m0I, but there is another term there, mu B sigma dot B, where B is the curl of A. As I say, this isn't straightforward. It takes a little algebra to get there. But this then becomes this result, and what we had done in B 3.6, of course, we didn't have the spin part of the story at all. What we had was just this. But that would come out of here, of this Dirac equation. If you put P, instead of P, you put P plus QA, and then do the reduction. Then you'd get this additional term. Now, if you compare this with this, it gives you a little bit of insight in the sense that you could say, well, this F cross P is almost like an effective B field. So often people say that the spin orbit term arises because an electron moving very fast in an electric field kind of sees an effective B field, which is F cross P, F is electric field, divided by 2mc square. And so in a large electric field, you can have a large effective magnetic field, which then gives you something like this. So that is, if you compare this and rationalize it in terms of something like this. But of course, that's not the derivation of this at all. The derivation is what we did in the last slide. That would be the method of how you would get there. Now, so to summarize here then, it's like in the Dirac equation, you have a 4x4 matrix H, and if you include potentials, U goes on this diagonal here, and vector potential goes in P plus QAs. And if you reduce it using the ideas we talked about, then you get a 2x2 Hamiltonian, which looks something like this. This is what we had before. Now, when you include spin, you get an I in front of it. There's a 2x2 matrix. And then there is this additional part that involves the spin matrices. This is called the Zeeman term, and this is the spin orbit term. So this is for electrons in vacuum. Now, if you want electrons in solids, then this part, I guess you have the EC, conduction band edge. And again, we are using the simplified one-band description here. You have a EC, and then instead of the free electron mass, you have the effective mass. And then you have this G factor of the solid that comes in to the Zeeman term. And this, you could replace, instead of this, you would have a term looking like this, which you could rationalize by saying that, well, if I have an electron confined in this XY plane, there must be an electric field in the Z direction that's keeping it there. If you thought of it that way, you can see why instead of F, you have a Z. And it looks similar. And this eta itself then is the Rashba coefficient, or the spin orbit coefficient, right? And as I said, in general, depending on what model you are using for solids, there could be more complicated description. What we'll talk about in this course is just based on this picture. Now, if you do not have any external magnetic fields, then there's no B or A, and so then you get something like this. This is our usual, without any electric fields, that our usual Hamiltonian. There's the I, and then there is this Rashba term for at the surface of a two-dimensional conductor, sigma dot Z cross P. So with that description then, we have the spin orbit Hamiltonian that we want to talk about. So what we'll do in the next lecture is see how you can translate it into the tight binding parameters. That is, what we had done earlier is, we had said, if you had this simple Hamiltonian, this EC plus P square over 2m, how you can choose your tight binding parameters, the on-site ones, the epsilon, and the nearest neighbor ones, this t, how you can choose it to match the dispersion relation to what you want. And we talked in 3.6 about how you could extend that to include vector potentials. What we'll do in the next lecture is talk about how you can choose these parameters so as to correspond to this spin Hamiltonian that we just talked about. Thank you.